Okay, so this is going to be our Algebra 2 Unit 1 Day 10 video. I'm just going to work through a few examples. So coming back here to the EQs, we're going to be talking about basically doing arithmetical operations, so addition, subtraction, multiplication, division, with actual functions, right? And, well, it's a lot simpler than it sounds. Okay, so for example, here's our first example we're going to look at. We've got three functions here. M, N, and P all are functions of X, right? So that means, and I mean, that's not necessarily what makes them combinable, but that means we can simplify them after we combine. So what do I mean by that? So first example here, what is M of X times N of X? Okay, so all we're really going to do is take m and n of x and multiply them together. So m of x times n of x is going to look just like this. So m of x, right, we see is right there. And then we're going to multiply that times n of x, right? And we're just going to end up with 72x squared. Okay. And in case you forgot, because we're multiplying two functions of x like that, x times x, well, that's x to the first times x to the first. So you would add the exponents, and that's why we get an x squared from all that. Okay. So let's look at the next one. Next one says, well, what about n times m of x? So now we're going to do n times m for short, right? And that's just going to switch us around. So now we're doing 12x, so that's n, times m, which is 6x, right? And we're going to get the exact same thing, 72x squared, right? Now we're being asked, well, what is p times m, right? So now we're doing p times m here. Okay, so that means we're going to have x plus 1, that's p, times m, which is 6x, right? And we can rewrite that to where it looks more familiar to us, just 6x times x plus 1, all in parentheses like that. And of course, we know already we're just going to distribute the 6x into the parentheses. So 6x times x, 6x squared, plus 6x times 1, which is just 6x, right? Okay, next example. What is m over n of x? In other words, we're dividing now, right? So m over n, right? So m over n is going to be 6x over 12x, right? And we would be able to simplify this further, right? So x divided by x will cancel, and that leaves us with just 6 over 12, which of course reduces down to 1/2. So m divided by n ends up just being a constant 1/2. That's pretty cool. Okay. What about, oh, let me back up. I'm getting ahead of myself. Okay, so it asks us, is there a domain restriction? Technically, yes, there is. Right here, we would have to say that x cannot be equal to 0. Okay, so even though we ended up simplifying, this would be called a removable discontinuity, and we'll get more into that later. But let's say I did, so this is m over n of x, right? And that equals 6x over 12x. Well, let's say I did m over n of 0, right? Well, that would be 6 times 0 over 12 times 0, right? We end up with 0 divided by 0, which is undefinable, right? It's nothing divided by nothing. Okay, so we would have to say, as a domain restriction, we would have to say that in our domain, x cannot be equal to 0 for this reason right here. Okay, we end up dividing by 0. Okay, so now let's get back on track. So and I underlined the wrong thing. I should have underlined there. But that was number 4, and that was our domain restriction. Well, now we're being asked the same thing here on number 5, n over m this time, n over m. So n over m this time, right? So that's going to be 12x over 6x. And of course, we know that's going to reduce down to 2. And then we're going to have to also say that we have a removable discontinuity at x equals 0. So we do not want x to equal 0 for the same reason that happened here. We'll end up with 0 divided by 0 again. Okay, so that would be our domain restriction. And let's see, running out of colors now. Okay, n divided by p. Okay, so n divided by p. So that would be 12x over x plus 1. And we see that uh, because of that, we can't simplify any further, right? So that's going to stay as is. So that's n over p, right? And is there a domain restriction? So what we're looking for here, when we're being asked about domain restrictions, we're looking for something that would make us divide by 0, which effectively means we approach something infinite. That gives us asymptotic behavior. Again, we'll learn a lot more about that in later lessons. But for right now, we all understand dividing by 0. Uh, I'm not going to say it's not good because it does happen in nature. That's how black holes are possible, for example. But anyway, I'm going off on a tangent. So, what would make us divide by 0? Right? Well, quite obviously, x cannot be -1 because if I put a -1 right here, I would have 12. Whoops. I would have 12x over. I shouldn't say that. I should have 12x, right? If we're plugging in -1 for x over -1 plus 1, well, that gives us -12 divided by 0, right? Which would give us -infinity, which means, yeah, we have to have this as our domain restriction here. Okay, and our last one, and I am completely out of colors to use, I'll just cycle back to green. Which operation was commutative? So obviously, multiplication of the functions was commutative, right? When we multiplied both times, right, we got 72x squared when we multiplied here. Okay, when we did division, so m over n was not equal to n over m, right? So the commutative property only went to multiplication, right? And we'll see that that also applies to addition here on this next example I want to show us. So just to prove that adding is also commutative, right? So f plus g, right? Well, that would be, and if we look here, we've got f and g. This is what I'm talking about. That would be equal to 10x plus 80 being added to 13x minus 20, right? And we see that we have no need for the parentheses. We'll go ahead and drop them. Our final answer, so combine like terms, and let me go ahead and just give you the visual of dropping, quote unquote, the parentheses because we don't really need them right now. You always still want to use them, okay? Just trust me, especially when you're doing something like here on number 5 where you're subtracting. But we know we're going to be able to combine these like terms. So 23x, this is going to give us positive 60. Okay, so that would be f plus g, right? Now, what do we get when we do g plus f? Well, that would be 13x minus 20 being added to 10x plus 80, right? Okay, so that's g plus f, g plus f. Okay, and again, we see we have no need for the parentheses, so I can go ahead and drop them. Nothing's being distributed in, so we can go ahead and start combining. So 13x, 10x, oh, I get 23x again, just like I did here. And then negative 20, positive 80, I get positive 60 again, like I did here. Okay, so adding and multiplying are both commutative, even in, just a purely algebraic sense. Okay, so on to our next example. So we're going to review a little bit on foiling because we're going to have to do that here, f times g, right? So if we're going to do f times g, well, that's going to be 3x plus 2 times 2x minus 1. Okay, so we're going to have to FOIL, and if you've forgotten, right, FOIL stands for first, outer, inner, last. Okay, so first, 3x times 2x is 6x squared. Outer 3x times negative 1 is negative 3x. Inner, that's going to be plus 4x. And last, that's going to be minus 2. And then all we're going to want to do from here is combine like terms. The only ones that are combinable are this negative 3x and the positive 4x. That's going to leave me with 6x squared plus 1x, or just x, minus 2. Okay, so f times g ends up just being 6x squared plus x minus 2. Okay, our next example is h of x plus f of x. Okay, so we're adding h plus f. Okay, so that would be equal to x squared minus 2x plus 8 plus 3x plus 2, right? We see no need for the parentheses, so I'll go ahead and drop them. And we're just going to combine like terms where applicable, right? So x squared combines with nothing, so that's just going to be x squared. Negative 2x, positive 3x, that's going to leave us with just positive x. And then the positive 8, positive 2, that leaves us with positive 10. Okay, so that would be equal to h plus f of x. Okay, then we've got g minus f. Okay, so g minus f, so this is where the parentheses are going to be important. So g minus f this time. So we've got 2x minus 1 for g minus f, right? And the parentheses on the left, we can go ahead and drop just because nothing's being distributed into them. But the parentheses here on the right, we cannot, because we see we're going to have to distribute this minus. And we've come into, we've seen this before when we were doing the systems, the linear systems, we were doing substitution. We would oftentimes have to distribute a minus like that. So our next line of work is just going to look like 2x minus 1 minus 3x minus 2. Okay, so minus 3x minus 2 after we distribute the minus. Okay, now we just combine like terms. 2x, negative 3x, that's going to leave me with negative x. Negative 1, negative 2, that is negative 3. And that would be g minus f of x. Okay, and then next one. So we've got f over g. So f over g of x, right? And that is going to be equal to f, so 3x plus 2 over g, 2x minus 1, right? Can't simplify anything here. There's no common factors or anything, but we can point out that there will be a domain restriction, right? So it's not so obvious, but our domain restriction would be that x cannot be equal to 1/2. Okay, and I can show you why. If I take the denominator, right? Because when we're looking for domain restrictions, that's what we want to focus on, because domain restrictions are often going to correlate to anything that makes us, any value of x that makes us divide by 0. So a real simple way to do that, if it's not painfully obvious, is to just take your denominator separately, 2x minus 1, and set it equal to 0. And if we just do some quick math, so add 1 to both sides, we see that we have 2x equals 1. Then we divide by 2 on both sides, and then we get x equals 1/2, which is where we've got here. So that means when x is 1/2, right, we would get a 0 in our denominator, and therefore we would divide by 0. And if I go ahead and plug that in, I'll do it real quick just to prove a point. So 3 times 1/2 plus 2 over 2 times 1/2 minus 1. Okay, so 3 times 1/2, that's 3 over 2, that plus 2. All of that over 2 times 1/2, well, that would just be 1, and we have 1 minus 1. So it doesn't matter what's going on here on top. That, by the way, so that would be 7 over 2, or 3.5 over, well, this is going to end up just being 0. And now we see we're dividing by 0, and we would end up with infinity, right? So we don't want to mess with that. Okay, so we would go ahead and just say our domain restriction is simply x cannot be 1/2. Otherwise x can be any other real number. Okay. Then moving on, f minus g, right? So f minus g, 3x plus 2. And then we've got that minus 2x minus 1. Again, we see, something similar to what happened on a previous example. So the parentheses on the left, we don't need them, but we do need them here on the term on the right. Okay, because we're going to have to distribute the minus inside the parentheses. So 3x plus 2 minus 2x plus 1. And now we're good to combine like terms. So 3x minus 2x, that's just x. Positive 2, positive 1, that's just plus 3. Okay, and then I'm going to skip this other subtraction example just because kind of redundant there. Let's look at h over g. Actually, yeah, let's skip that one too. I think we've seen enough division examples and examples with domain restrictions. So now let's look at a word problem example. So here we've got another Jumpy Jeffrey Paranoid Pete problem. They're working for Elon Musk, testing a a jetpack. Um, the jetpack accelerates Jeffrey at a rate of 32 feet per second squared, or 32 feet per second every second, right? So every second he's going 32 feet per second faster. Okay, that's what acceleration means. And then when engaged, the turbo booster should, in theory, accelerate Jeffrey at a rate of 16 feet per second squared on its own. Okay, so being more of a math buff than a physics nerd, Pete is unsure what the relationship will be with the booster. If it'll be a additive, if it'll be an additive relationship or a multiplicative relationship. Okay, so first, let's find a function j of t for Jumpy Jeffrey's initial acceleration rate without the booster, only with the jetpack's original formulation here. So we would say j of t is simply equal to 32 feet uh, per second every second. So 32 times t, the number of seconds, right? So that's relatively simple. Okay. Now a function for the booster on its own, right? Its sole acceleration rate. So that one would be booster's acceleration as a function of time would be equal to 16 feet per second every second, right? So pretty simple there. Then let's get into calculating j plus b of t, and let's see what this would mean, right? So j plus b would be equal to 32t plus 16t. So that would just be 48. Oh, God. That would just be 48t, right? Because we would just combine like terms, 32t plus 16t, right? So that would be j plus b of t would be equal to 48. So now we'd be we'd be accelerating 48 feet per second squared. So 48 feet per second every second. So we're going 16 feet per second faster, right? Now, if we say multiplicative, right? So j times b. So I have no idea off the top of my head what 32 times 16 is. So 32 times 16, that would be 512. So j times b, right, of t would be 512, and then t times t, so t squared, right? So now we're saying that would be 512 feet per second every second squared, right? So that's, and I'm not much of a physics buff myself, right? But to me, that means we're no longer talking about acceleration. Uh, we're talking about even a higher order than jerk, which is the third higher order. Uh, I guess you would call it delta position, right? So yeah, so that seems kind of ridiculous. If this ends up being, so if it ends up being a multiplicative relationship, right? This right here tells us that Jumpy Jeffrey is going to die a horrible death. Okay, so pretty sure, so moving on to number 5, pretty sure that we're going to have an additive relationship based on what we see here, because this right here just seems a lot more realistic. Okay. And it's probably obviously not that simple. Like I said, I'm not a physics buff, but if this is anything relative to vector mathematics, you would simply just add, assuming both uh, forces are being projected in the same exact direction. Okay. So that's all for this video. Like always, shoot me an email or just come and see me if you have any questions. Goodbye.